Good morning friends, welcome back. In our previous lecture we were discussing about how CL alpha of an aerofoil and wing differs. When we say wing, we know it's of finite aspect ratio. So we have derived a relationship between the CL alpha of aerofoil and CL alpha of wing. Let us say this is your zero lift line, angle of attack is defined with respect to the zero lift line of an aircraft, and say this is your CL, y axis represents your CL variation and alpha is along the x axis here, right. This is for aspect ratio infinite, right. Say this curve represents the variation of lift coefficient with angle of attack for an aerofoil, right. Now let us say this is for a finite aspect ratio wing, which is AR1. So this represents the CL alpha curve for wing with aspect ratio 2. Wing with aspect ratio AR2, right. Now say this is your increasing order of aspect ratio, okay. Now let us assume we have used the same aerofoil to build a wing, right, and what should be my angle of attack for aerofoil to achieve a particular CL, and what should be the corresponding angle of attack for, let us say, if I want to achieve a particular CL, what should be the angle of attack that I need to trim my aircraft for an aerofoil and for that of a wing, right. So let us say this is your required CL, say design CL or CL required. So for this particular curve, say I require this angle of attack, which is alpha naught. So alpha naught represents the angle of attack required by this aerofoil to achieve this particular CL, right. So this is your alpha naught, right. Now let A naught be the CL alpha curve for this aerofoil, where A naught is equals to d CL by d alpha of aerofoil, that is CL alpha, which is 2d. Now let us assume we have built a wing using this particular aerofoil without any geometric twist and aerodynamic twist, right. Now what happens if I want to achieve the same CL here, right, I need to trim the aircraft at a angle of attack, right. Let us say this be alpha, right. This point represents alpha comma 0, right. So this point represents 0 comma CL design, okay. Now for a wing we have an increased angle of attack compared to that of an aerofoil. This increment is due to the induced angle of attack which we have witnessed during our previous lecture, alpha I, right, where this alpha I according to lifting line theory is equals to CL by phi E AR, where E is the Ostwald's efficiency factor and AR is the aspect ratio B square by S. Both are non-dimensional parameters here, right. Now the CL design or the CL you can achieve by aerofoil. Since it's a straight line, we can assume this is in the linear domain of angle of attack, or the variation of CL with angle of attack is linear up to this, say whatever the CL that we have considered is in the linear domain, okay. So now from the straight line equation we have y is equal to mx plus c, that Cl is equals to c is 0 here, y intercept, since we are defining this angle of attack with respect to 0 lift line. So a naught is the slope of this curve times the corresponding x alpha naught here. So this is achieved by aerofoil, right? The same Cl I can achieve by the wing. Say A is the lift curve slope of this particular airfoil, particular wing. Let A be the lift curve slope, which is 3D lift curve slope, where A is equals to dCl by d alpha, this Cl alpha 3D. So capital L here represents, capital Cl represents 3D lift curve slope Cl alpha, so whereas small Cl represents for 2D Cl alpha here. Okay. So this equals to slope of this wing, lift curve slope of this wing, multiplied by the corresponding x, that is alpha here. Right. So this alpha is alpha naught plus alpha I. Right. So this, say this is my equation 1 and this is my equation 2. Right. Now comparing 1 and 2, since we are producing that same design Cl by using a airfoil and wing, so the lift is same in either the case. So from this equation 1 and 2, what we have is A naught is equal, A naught into alpha naught is equals to A into alpha naught plus alpha I. Okay. From here A naught is equals to A into 1 plus alpha I divided by alpha naught. Right. This implies A naught is equals to A into 1 plus, what is alpha I? I here is Cl divided by pi E AR. Right. This equals to A naught is equals to A into 1 plus, what is Cl? So we can achieve Cl from this aerofoil by trimming it at a particular alpha naught, right. So that means the Cl that I can achieve here is by A naught into alpha naught from the aerofoil into alpha naught. This implies A naught is equals to A into 1 plus A naught by pi AR. A is equals to A naught by 1 plus A naught by pi E AR, which is Cl alpha Cl alpha 3D is equals to Cl alpha 2D by 1 plus Cl alpha of airfoil by pi A. So this is well valid in the subsonic flight regimes, right. This is a relationship between wing Cl alpha and airfoil Cl alpha. Now let us look at some of the, this some of these aerofoils and their lifting characteristics. Right. So this data that we are going to present is obtained from the wind tunnel test. So the reference that you can consider for this is Theory of Wing Sections by Abbott. So the first aerofoil here, we also discussed this during our earlier example. It's a NACA 2412 airfoil. Now the question is how to calculate Cl alpha, right? How this data is obtained? You can see here. So this is obtained for different Reynolds number, which means assume that you have used the same aerofoil, but you have performed this test at different velocities inside a wind tunnel. So let us dedicate one lecture for one lecture to figure out how to measure this CL, CD and CM from wind tunnel test, right? Or say how a wind tunnel test is performed, how these measurements were taken for aerofoil as well as wing. Now here let us consider any one of this Reynolds number, say it is 3 million Reynolds number here in the first. So the corresponding marker here is the circle. So we need to follow the circle data to achieve the corresponding characteristics at 3 million Reynolds number, right? So now the question is how to find what CL naught, CL alpha, alpha max, alpha stall, CL max, right? Alpha at which CL is 0. How to find CL naught of airfoil, CL alpha of airfoil and alpha at which CL is 0 and CL max of airfoil and alpha stall and so on, right? So given the data, let us see how to get these parameters. Now coming back to this 2412 data, we know what is 2412, right? Just a quick recap. The 2 represents the maximum camber in percentage of chord, right? 4 represents location of maximum camber in tens of chord, that is C by 10, and 12 represents maximum thickness in percentage of chord. See, so this is equals to maximum thickness is 0.2 C for this particular aerofoil, and the corresponding location is 0.4 C, and the maximum thickness is 0.12 C, which is 12% here. Now what is CL naught? CL at which alpha is 0. Now let us look at the angle of attack at which so this is your 0 angle of attack, you can see here. Now let us take the corresponding value of CL, that should be your CL naught. So the corresponding value is something here, which is, say, so this y axis represents the section lift coefficient here, CL, right? So this is your 0 CL, and there is an increment to 0.4 here that you can see. So till that increment there are 4 steps, which means this each line corresponds to 0.1 CL here. So the corresponding CL naught from here we can notice it as CL naught is, so which is 2-dimensional, CL naught is 0.21 approximately, which is approximately, right? And say how to find out the CL alpha here, right? So we will find out CL alpha while solving some of these examples. Okay. Now let us say how far this CL alpha is linear. So for this particular curve, which is achieved by performing this test at 3 million Reynolds number, say up to here. So up to here it looks pretty linear, which is approximately 10 degrees angle of attack, right? Up to 10 degrees angle of attack, this curve looks pretty linear, which you can model it as CL is equals to CL naught plus CL alpha into alpha, right? So this particular regime you can consider the linear variation of CL with angle of attack. And now we have to look at alpha at which CL is 0. This is your origin, say 0 0. Oh, I am sorry. I'm sorry. Now this is your origin. Now you need to find out alpha at which Cl is 0. That means this is the point where Cl is 0. Right? This is the point where Cl is 0. So the corresponding angle of attack for this is approximately -2 degrees. Right? So alpha at which Cl is equals to 0 is -2 degrees. This particular airfoil stalls at an angle of attack approximately 15 degrees. Right? Alpha stall is approximately 15 degrees, and the corresponding value of Cl is 1.6. So Cl 2D max is 1.6. CD is equals to CD naught plus K Cl square. Right? Now this particular plot represents the variation of CD with CLC. It's almost parabolic variation. So this particular equation or this particular formulation will definitely fit this particular this data CD whatever the data internal data that you obtained here. Now what is CD naught? The profile rack here, which is at Cl is equals to 0. So what is Cl 0 here? So this is your Cl 0, and the corresponding drag coefficient is 0.1 approximately. So CD naught from of this aerofoil is 0.01. So you see this is a moment about aerodynamic center, variation of moment about aerodynamic center with Cl, right? Although the lift changes, when do lift changes? When the angle of attack changes, lift coefficient is changing when the angle of attack changes, right? So here as so this we can infer as the angle of attack changes or and hence the Cl changes, the pitching moment almost remain constant. See, it is a constant value. Although there is a variation in Cl, the value of this pitching moment remain constant at about C by 4. This the corresponding aerodynamic center for this is C by 4. So this moment is about C by 4, quarter chord of that aerofoil. So the value of this is about -0.04. So Cm about AC of aerofoil is 0.04, right? -0.04. Please make a correction. It's -0.04, which means it's a positively cambered aerofoil. So for positively cambered aerofoils, the CMAC is negative. Right? Now let's go to the next data set, which is 4415. It's again a 4 series aerofoil. So you can see here. So this is the variation of Cl, Cm with alpha, and here to the right you have Cl, CD, Cm variation with Cl, right. Here what will be the Cl naught for this aerofoil? Cl naught of this aerofoil is 0.4. So let us look at the next aerofoil, which is also a 4 digit NACA 4415 airfoil, right. So we know the maximum camber is 0.4 C here, and the location of 0.04 C, and the location of maximum camber is about 40% of the chord, and the maximum thickness is 15% of the chord, right. Now for this aerofoil, what will be my Cl naught? So we need to select first the Reynolds number of our interest. Let us say 3 million is our current interest. 3 million Reynolds number is our current interest, and the corresponding Cl at which alpha is 0, which is our Cl naught, is approximately 0.4. So this 0.3 million corresponds to this data that is plotted with the circular marker. So, this corresponding CL naught is 0.4. In our previous example, and say in the what is alpha at which CL is equals to 0 for this aerofoil? So, this is approximately minus 4 degrees. This is the point at which this curve touches the x axis, which is like CL is equals to 0 and the corresponding angle is minus 4 degrees. And we have to figure out what is the CL max of this. Say what now can we identify the linear regime of angle of attack? So, for this circular marker, the one which is above here, the one this is the CL versus alpha data at 0.3 million Reynolds, at 3 million Reynolds number, right. So, here we can observe this is linear up to say this particular point, beyond which there is a slightest non-linearity, and then a stall occurs at is alpha of 15 degrees, 14 degrees say we can say alpha stall is approximately 14 degree, and this is your point for CL naught, that is 0.4 alpha. You have CL max, which is in this case is 0.5 1.55 around, right. And what is the CL, so what is the linear range of this CL variation with angle of attack? So, from 0, if you can observe from this plot, it is varying from minus 2 in fact, right, or minus 4 degrees, to say approximately 10 degrees. So, alpha even for minus 8 degrees, minus 8 and minus 10 degrees, it is still behaves linear here, minus 12 degrees it still behaves linear. So, less than or equal to minus 10, let us say alpha 10 and minus 10, these are the boundaries of linear regime of angle of attack, right. So, and the corresponding CD value for this is CD naught. If you want to find CD naught, the CL is 0 at this particular location. So, this is approximately for 3 million Reynolds number, it is 0.0079 or 8, that is CD naught is approximately 0.008 for an airfoil, right. And what is the CM about aerodynamic center? CM about AC is equals to 0.1 minus 0.1 approximately, right. So, you can see here with angle of attack for in the linear regime of angle of attack, the CM almost remains constant with angle of attack, right, in this linear domain. So, the aerodynamic center about, we can consider this moment reference point as the aerodynamic center. Why? Because the pitching moment is remained almost constant with angle of attack in this particular regime. So, this is the CM variation with angle of attack. Similarly, there is a 5 series aerofoil 23012. You can also find CL naught, CL alpha. So, the CL naught for this aerofoil is about 0.1 and CL alpha is about 6.45. We will find out how we will figure out how to find CL alpha when solving some examples. The alpha stall in this case is about 15 degrees and CL max is 1.5 and the corresponding CL max is 1.5 at alpha stall of 15 degrees and Cm about aerodynamic center is minus 0.0125. So, we are talking about 3 million Reynolds number, data at 3 million Reynolds number, and CD naught is 0.07 and alpha at which CL becomes 0 is minus 2 degrees in this. And there is another 5 series aerofoil 23018. You can see the pitching moment is constant, almost constant. Cm variation with Cl is constant here, if you can see. So, and the corresponding value is almost 0 here, 0.01 say 0.01. And the CD naught value for this particular 23018 aerofoil is approximately 0.007, which is almost same as 23012 and 23018. So, although there is a increase in the thickness ratio T by C, but there is no increase in drag coefficient, profile drag coefficient. Now comes the 6 series aerofoil. See, there is a huge difference. The main thing that we can notice is a drag bucket. This is what we discussed in our earlier lectures. So, in our previous case where the CD versus CL, if you look at drag polar plot, there is no significant drag bucket. You can't witness a significant, although for some portion it may remain constant, almost constant, but not exactly the same as what we are witnessing at 6 series aerofoil, right. So, right from here we do not see a significant drag bucket, but for the 6 series aerofoils you can see the CD almost remains constant with variation of CL or angle of attack here. And similarly, you can find out for this 641-212 aerofoil, you have alpha CL naught is 0.1 and alpha at which CL becomes 0 is minus 1 degree and CL max is approximately 1.5 and the alpha stall is 15 degrees. This is 1.5 and corresponding alpha stall here is approximately 15 degrees, right, and Cm about AC is minus 0.025. So, the value that you get Cm at different alpha is, this is Cm at alpha 0, right, this is Cm at CL 0. Now, similar drag bucket we can also observe with 653-418 aerofoil. Now, let us look at this significance of this subscript 3 here, right. Now, from the nomenclature 65418 we can find out what is the design CL for this particular aerofoil, which is CL design of this aerofoil is 0.4, right. This 4 represents in tens of, 4 multiplied by 1 by 10 represents the corresponding design CL of this aerofoil. Now, let us take this 0.4 here, consider 0.4 CL and say now this subscript 3 represents the regime in which CD remains constant, right, for about this CL design, which is plus or minus 0.3 of this CL design, plus or minus 0.3 of this CL design. So, in this regime CD will almost remains constant. Let us see whether it is true or not. So, 0.4 minus 0.3 is 0.1 approximately. So, up to this point the CD is almost flat, that is CL design minus 0.3, and then say CL design plus 0.3 is 0.7. So, we can also consider this regime as a constant CD regime, right. So, this is the significance of this drag bucket here. right. That happens, this you can, there is a significant drag bucket for 6 series aerofoil, and the nomenclature will help you to select the corresponding aerofoil based upon your CL design. Let us take up few examples to find the relationship between wing CL alpha and aerofoil CL alpha, right. Let us take the first example. Consider the following data of a wing alone UAV. So, there is some dimensional data is given here, which is B is 10 meters, area, platform area is 11 meters square, and the Ostwald's efficiency is 0.75, and CD naught of the wing total UAV is given as 0.02, right. Assume a NACA 2412 aerofoil is used to develop this UAV, or since it is a wing alone, we can say develop this wing. Find CL CD of the UAV at alpha is equals to 3 degrees, 5 degrees and 7 degrees. When you say CL CD here is for the entire UAV, right. And now, how to solve this question? So, CL is equals to CL naught plus CL alpha into alpha of the wing, right. And what is CD? Once you have CL, if you know CD naught, KCL square, right. You can use drag polar of the wing and you can find the corresponding CD at this particular CL, right. So, what is this CD naught is given, right. So, CD naught is given as 0.02, and K, can we find K here? Induced drag correction factor 1 by pi E AR, right. So, we know we have span and area, platform area. We need to find what is the corresponding aspect ratio. What is aspect ratio here? AR is equals to B square by S, 10 square divided by 11, that is 9.09, right. So, 1 by pi E AR is, so 1 by pi into 0.75 into 9.09, that is 0.0466, right. This is the value of K. Now, you know what is K, you know what is CD naught. What is CD naught here? 0.02 plus 0.0466 into CL square. Now, for different values of CL, you will get the corresponding CD. So, when do you get different values of CL? When you have different angle of attack, say 3 degrees, 5 degrees and 7 degrees here. But you need to find out what is the CL alpha of this wing and CL naught of this wing, right. For that, the information given is, this is made out of 2412, NACA 2412 airfoil. So, if we go back to NACA 2412 airfoil here, what is CL naught of this airfoil? Which is 0.21. So, CL naught I can write down here as CL naught of airfoil is 0.21, right, and alpha at which CL is equals to 0 is minus 2 degrees, which is this point, this particular point. At this point we have CL naught, and what is CL alpha of this plot? Say this plot we can safely assume linear till 8 degrees angle of attack, right. So, CL alpha 2D is equals to CL at alpha is equals to 8 degrees minus CL at alpha is equals to 0 divided by 8 degrees minus 0 into pi by 180, you will get it in radians, right. So, what is CL at 8 degrees? CL at 8 degrees is 1.1 approximately. So, this particular point is 1.1. So, CL comma alpha, you have at alpha is equals to 8 degrees, what you have is 1.1, and at alpha is equals to 0 degrees, what you have is 0.21 comma 0. So, by using this, since it is a straight linear equation, we can find the slope of this curve, right, y2 minus y1 by x2 minus x1. CL alpha 2D of aerofoil is equals to CL value at 8 degrees. CL value at alpha is equals to 8 degrees minus CL value at alpha is equals to 0 by 8 degrees. So per degrees I am converting it to per radians. This is alpha is equals to 8 degrees, you have 1.1 approximately minus 0.21 divided by 8 into 5 by 180. So this turns out to be 6.374. Right? This is your CL alpha 2D. And the other important, yes, once you have CL alpha 2D, you can find out CL alpha 3D. CL alpha of this wing, this equals to CL alpha 2D divided by 1 plus CL alpha 2D. Right? 6.374 divided by 1 plus 6.374 into 1 by pi r is 0.0466. This equals to 6.374 is 4.7. 4.9123. So CL alpha per radian of this wing, entire wing, is 4.9123. You have CL alpha here 4.9123 per radian. Right. Now we need to find out what is CL naught to find out CL at different alpha as well as CD at different alpha. Right. So how to find CL naught? So the assumption that we make here is, since we are making this wing out of this aerofoil, right. So we have CL versus alpha plot, right. This is for, say, aerofoil, okay, and we are making this wing out of this aerofoil. The assumption here is the alpha at which CL is 0 for aerofoil will remain same for the wing as well, right. So this is the point at which alpha CL is equals to 0 will remain same for wing as well as aerofoil. This is the assumption. So this is the alpha at which CL is equals to 0. So this remains same for infinite wing and a finite aspect ratio wing as well as infinite aspect ratio wing, right. Okay. Now with this assumption, we know what is CL alpha of this curve. So we got CL alpha 3D, and you know this point, we need to find this point. So this particular point is CL alpha at which CL is equals to 0 comma 0, and this particular point is CL naught comma alpha is 0 comma CL naught, 0 comma CL naught. So you have 2 points, you know the slope, like you don't know one of the point here, you can straight away find this CL naught, right. So this CL naught is equals to CL naught 3D is equals to CL alpha minus CL alpha 3D into alpha at which CL becomes 0, right. That is what you will end up solving that equation, right. So what is CL alpha 3D here is 4.9123 into alpha at which CL is equals to 0. So from the aerofoil data we can find alpha at which CL is equals to 0 is minus 2 degrees, right. So minus 2, is it right? We need to we considered CL alpha as 4.9123 per radian. So you need to convert this alpha from degrees to radians. So this is 2 into pi by 180. 0.17115 CL. Now substitute this in this equation 1, say this is your 1 and say this is your 2, right. So from equation 1 what we have, CL naught is 0.175, 0.1715 plus CL alpha is 4.9123 into alpha, right. So alpha should be in radians here and CD is equals to 0.02 plus 0.0466 into corresponding CL square. Now we need to find this at 3 different trim conditions, that is alpha 3 degrees, alpha 5 degrees, alpha 7 degrees. Now if you substitute alpha 3 degrees, what you are, so say this is alpha, this is CL and the corresponding CD. Say at alpha 3 degrees what you have, CL is what is 0.42, 0.4287 is the CL and the corresponding CD is 0.0286. Right. So at 5 degrees the CL value is 0.6002 and CD value is 0.0368. And at alpha 7 degrees CL is obtained as 0.7716 and CD is 0.0478. So all these values are obtained by using these two equations, right. So what we have done, given a wing planform geometry and Ostwald's efficiency factor as well as profile drag coefficient. So we figured out what are the CL alpha of this wing and CD of this, CL naught of this wing, and then we calculated what is the corresponding lift coefficient at different angles of attack as well as the drag coefficient at different angles of attack. So it is given that this wing is made out of NACA 2412 aerofoil, right. So from this aerofoil data we have figured out what is the CL alpha of this aerofoil and alpha at which CL is equals to 0 for this. So using those two we found out CL naught of the wing. Initially we figured out what is CL alpha of this wing and then the CL naught of this wing, right. So substituted those two parameters in this equation, we will be able to find out the corresponding CL and CD at different angles of attack. Now what is the why we need to find CL and CD in the first case? No, you will appreciate as we progress. Once we start discussing about what should be the lift or design CL, right, to sustain a particular weight at a given altitude, right, how to design the wing, that means how to select a planform geometry. During that time you need to have a design CL, what should be your design CL, right. So when we discuss those concepts you can appreciate this particular exercise and say which power plant do you need to select that requires the information of CD, right. So during various phases you need to move at different velocities and different flight conditions. So which power plant to be used, how do you find? You first gather the information about what is the requirement of the system. The requirement of the system is drag. So to calculate drag you need to find what is the corresponding CD. Now let us consider this example too. The CL design required to trim the following wing alone UAV at 3 degrees is estimated as 0.334. Suggest the aerofoil to be selected for this particular UAV, right. And it is also given CL alpha at which CL is equals to 0 is -2 degrees and the Ostwald's efficiency is 0.75. Now this is the planform that has been given. The UAV is with a triangular planform here, right. So we know what is the span of this and a leading edge sweep of 45 degrees is given, right. With this information we need to find out, we need to suggest an aerofoil, which means how do you suggest an aerofoil? In terms of lift and drag characteristics, right. say lift characteristics here, we need to give what is CL alpha 2D of the aerofoil should be, and say CL naught of the aerofoil, right, CL naught 2D, and say alpha at which CL is equals to 0, right. This is already given, because for wing as well as airfoil it will remain same here, that is the assumption that we have. Okay. Now first figure out what is given here, like the span is 1.5 meters, right. If what is the relationship between CL alpha 3D and CL alpha 2D? CL alpha is equals to of wing is CL alpha of aerofoil by 1 plus CL alpha of aerofoil divided by pi e air. So what you need is CL alpha 2D, right. How to find CL alpha 2D? Plan form, right, with a span of 1.5 meters and leading edge sweep of 45 degrees, and with the leading edge sweep of 45 degrees. Now I need to find out what is CL alpha 2D, right, of the aerofoil from the wing data. So how to get wing data here in the first case? So CL is equals to CL design is equals to CL alpha into alpha trim minus alpha at which CL is equals to 0. Can we do this? What does this equation mean? Assume that this is the CL versus alpha of your aircraft or the wing, right? This is your CL versus alpha. The information that is given is CL design, right? CL design is given as 0.334, and this design is achieved at an angle of 3 degrees, at an angle of attack of 3 degrees. Say at 3 degrees, this is your CLD. That means you know this point, right, and you have the information about this alpha at which CL is equals to 0, right. This point corresponds to alpha at CL is equals to 0 comma 0. You know this point, that is 3 degrees comma CL design, right. From here you can find out what is CL alpha, slope of this curve, right. So CL alpha of the wing is equals to CL design is 0.334 divided by 3 minus 2 degrees, right. This implies CL alpha of the wing is 0.334 divided by 5 into pi by 180, which in radians. So here it is in degrees, it is per degrees, here it is per radians, which is equals to 3.8273 per radian, right. Now you have CL alpha 3D. Now can we find out CL alpha 2D from here? So how to do this? Can we manipulate this equation? This implies CL alpha into 1 minus CL alpha 3D, CL alpha divided by pi EAR is equals to CL alpha 3D, right. If you take this to your left hand side or multiply this equation by this denominator, right. So and then taking this second term to the left side, to the right hand side. So what you have here is, so this implies CL alpha 2D is equals to CL alpha 3D divided by 1 minus CL alpha 3D divided by pi E air. Now substituting these values of CL alpha 3D is 3.8273 and 1 minus 3.8273 divided by pi into what is Ostwald's efficiency factor 0.75 into we need to find what is the aspect ratio of this wing. So how to find aspect ratio of this wing? We know aspect ratio AR is equals to B square by S, right. So we have the span, we need to find the area of this particular planform. So how to find the area? Half base into height, half span into say CR root chord here. So what is the root chord here? So when say this angle is 45 degrees, this is also 45 degrees. You know this span, you know this semi span which is 0.75, right. So tan 45 is opposite by adjacent. So this particular height will also become 0.75, tan 45 is 1, right. This particular height of this or the root chord of this triangular wing is 0.75. So you have half base into height, you can simply substitute 1.5 into 0.75. So S is 0.5625 meter square, right. So the corresponding aspect ratio is 1.5 meter square divided by 0.5625. This is 4. The aspect ratio turns out to be 4. Now substituting this aspect ratio in this equation, you can find out what is CL alpha 2D. CL alpha 2D is 6.4459. Now you are able to find what is the CL alpha 2D of this airfoil. Now we need to find what is the CL alpha, CL naught of this airfoil, right. Say this is my airfoil data, right. Aspect ratio is infinite. Here we have aspect ratio is equals to 4 for this wing. So now we need to find out this y intercept of this airfoil. We know the slope of this airfoil, just now we have figured it out as 0.4459. So we need aspect ratio to calculate that CL alpha. So we have figured out area from the given geometry. This is the relationship we have started with 2D CL alpha and 3D CL alpha. So we figured out 3D CL alpha based upon the design CL as well as the angle of attack which this aircraft has to be trimmed or that CL design has to be achieved. Now we have 2D CL alpha, right. You know the slope, you have this point alpha at which CL is equals to 0, right, which remains same for airfoil as well as wing, that is assumption. Now using the slope and this we can find out what is the CL naught of that. So CL naught of airfoil is equals to minus CL alpha of airfoil into alpha at which CL is equals to 0. This is minus 6.4459 into minus 2 degrees. So minus 2 degrees is given in the question. So this equals to, so this is in degrees but the slope is in per radian. So I need to convert it as, I need to multiply this by pi by 180. 0.225. Right. CL naught is 0.225 for an airfoil, and so see, now let us see what is what are alpha at CL is equals to 0 and CL naught of airfoil, or say CL naught and CL alpha for airfoil and wing. So for airfoil it is minus 2 degrees, and yeah, here it will be same. What is CL naught of airfoil? is 0.225. What will be CL naught of the wing? So we can find out, right, that CL naught is equals to minus CL alpha into alpha at which CL is equals to 0. You substitute the wing CL alpha, you will get the corresponding CL. 0.1335, right, and CL alpha of the wing is, of the airfoil is 6.4459, of the wing is 3.8273. These are per radian, per radian, per radian, per radian. See, lower the aspect ratio, lower is the CL alpha of your wing. You can observe that, right, here. The same airfoil is used to build a wing which is of lesser aspect ratio wing. So, aspect ratio is about 4 here. So, the CL alpha drastically reduced, right. Now, say if I increase the aspect ratio, now let us consider example 3 here. Consider the following UAV is designed using NACA 653418 airfoil. If the CL design of this UAV is 0.4, find the corresponding trim angle of attack. So, the plan form of this UAV is given, which is of 2 meter span and 0.3 meters tip chord and the leading edge sweep of 31 degrees, right. So, we need to find the trim angle of attack, right, first. So, if the CL design is known, then we can express the CL of this wing as CL naught plus CL alpha into CL alpha of the wing into alpha trim. So, this alpha trim is equals to CL design minus CL naught divided by CL alpha, which is 3D of wing, and this CL naught is also for wing, right. Now, so what are unknown here? So, CL design is given, which is 0.4 here, and we need to find out what is CL alpha 3D and CL naught of this wing. So, another information given is airfoil, right. Regarding airfoil, which is used here is NACA 653418. Right. Now, we need to find out, in order to find out CL alpha 3D, we need to know what is the airfoil CL alpha. Okay. So, as well as the aspect ratio and Oswald's efficiency. Say the Oswald's efficiency is about 0.75, right. So, we need to find the aspect ratio of this wing. First, how to find the aspect ratio? We know AR is equals to B square by S. So, we need to find what is area here. So, to find out area, I need the root chord, right. I need to know what is this root chord. So, how to find this root chord? So, say this is, say up to this it is 0.3, right. Say this entire thing is CR, entire chord at the root is CR. So, this is like CR minus 0.3, right. Now, I know leading edge sweep of 31 degrees, I know the span here which is 1 meter, right. So, we know aspect ratio is equals to B square by S, right. So, to find this aspect ratio I need to know the area here. To find this area I need CR here. So, tan 31 degrees is equals to CR minus 0.3 divided by 1. So, this implies tan 31 is approximately 0.6, is CR minus 0.3. This implies root chord is 0.9 meters. So, CR here is 0.9, right. Once I have CR, I can find out what is the area of this wing. What is area of this wing? B into Ct plus Cr by 2, which is equals to, otherwise B by 2 into Cr multiplied by 1 plus lambda. So B is 2 meter span into 0.3 plus 0.9 by 2, which is 1.2 meter square, right. So substituting this span 2 meter square and 1.2 meter square area, we will get to know what is the corresponding aspect ratio. So aspect ratio here is 4 divided by 1.2, 3.33. So aspect ratio again is a low aspect ratio wing here. It's a low aspect ratio wing UAV. So you know what is aspect ratio. Now what you need to know is CL alpha 2D. Here. This is CL alpha 2D. Now say, let us go back to this aerofoil data NA 653418. Right. So this is the airfoil. So we can see here the variation of lift coefficient with angle of attack as well as pitching moment coefficient with angle of attack, and this particular plot represents the drag polar, and this is Cm versus Cl about C by 4, or the aerodynamic center here. This is about C by 4. Okay. Now what we need to find out is CL alpha of this wing first. So let us first consider what is CL at alpha is equals to 0. That is CL naught is 0.3. See, this is a CL at which alpha is equals to 0. Right. So this particular point, like CL and alpha for 0 degrees, this is 0.3. Now how far we can consider this linear here? So let us say if we look at this curve, so we are talking about this curve at 3 million Reynolds number, right. So it is with circular marker, and see if you consider that curve here, how far this is linear. So here about this point, so maybe up to this point we may consider this as a linear curve, right, straight line. So the corresponding angle of attack is approximately 6 degrees. So 6 degrees, because beyond which there is a change in slope, right, it becomes non-linear. Now at this 6 degrees angle of attack, the corresponding CL value is 0.9. So how to find out the CL alpha of this curve? y2 minus y1 by x2 minus x1, that is CL at alpha is equals to 6 degrees is 0.9 minus 0.3 divided by 6 into pi by 180. So what is the answer for this? 5.73. 5.73 per radian, right. Now we got to know what is alpha, CL alpha of this plot, and let us also look at alpha at which CL is equals to 0. So this particular point is the alpha at which CL is equals to 0, which is approximately 2 degrees, right, 2, 4, 6, 8, okay, it is approximately minus 2 degrees. Alpha at which CL is equals to 0 is equals to minus 2 degrees. Okay. Let us take this information and find out what is the CL alpha 3D, which is the CL alpha of wing made out of this aerofoil. Now from here we got to know, using this NACA 653418, CL alpha of this aerofoil is 5.73 per radian. So this is the CL alpha of this aerofoil. Now substituting this in this equation, what you will get CL alpha 3D is approximately CL alpha 3.3165. 3.3165. Right. So to calculate alpha trim, we need another variable here, CL naught, right, or another parameter CL naught that we need to find out. So CL alpha is 3.3165. Now how to find out CL naught of this wing? again from the airfoil data we have alpha at which CL is equals to 0 is approximately minus 2 degrees. Alpha at which CL is equals to 0 is approximately minus 2 degrees, which will remain same for wing as well as the airfoil. Okay. Now, CL naught of wing is minus CL alpha of wing into alpha at which CL is equals to 0. This equals to minus 3.3165 into minus 2 degrees into pi by 180, because this slope is in per radian, right. So, the corresponding value of CL naught is 0.1157. Now, alpha trim can be estimated from this equation as CL design given is 0.4, that is CL design given CL design is 0.4 and E is 0.75 here. So, this is like 0.4 minus CL naught, which is 0.1157 divided by CL alpha of this wing, which is 3.3165, 0.0857 radians. So, in degrees it is approximately 4.9 degrees. Right. So, this is the angle of attack which the aircraft will be trimmed to attain this particular CL.